Welcome back. Now we're going to look at the linear or integrating factor method from section 2.3. Let's start off, as with any method, with the check. For the linear method, we're looking for a first-order differential equation, which is written in the form x prime plus p of t times x equals q of t. Now, this is checked from the standard form, where you collect all the unknown terms, as capital F is just some general function or collection of x prime, x, and t. All the unknown terms on the left, and any leftover terms you put on the right. Now I say unknown terms to represent all the dependent variables, x, x prime, and combinations of those, and the known terms as the independent variables or functions of the independent variables, including constants. So that's what we use to check. In a similar way, to verify that a differential equation is separable, you use the slope form, where you solve for the derivative. In this case, you solve for the known terms. In a sense, you put all the unknowns on one side and the knowns on the other. Okay, so once we have our differential equation written in this form where we know p of t and q of t, and we've grouped them together to get a 1 in front of the x prime, then our first step in the computation is to compute mu of t, which we call the integrating factor. That's a Greek letter, mu. One possible reason why it's a mu is because you multiply with this integrating factor. But it could be another reason. Tradition is probably another reason why we use this particular Greek letter. To compute it, you take the p of t function, you integrate that function of t, and then you exponentiate what's left over. Now, that integral will leave you with our integrating constant, which means you'll have an infinite number of these integrating factors. But we actually don't need to know all of them. We only need one integrating factor because it's a helper function. So we can choose the simplest version of that integrating factor that is most helpful to us. So choose just one. And then you multiply the whole equation by that one integrating factor. Once you have it multiplied through, you combine the unknown terms using a reverse product rule. Let's look at that for a second here. When you multiply through by mu, you have mu of t times x prime plus mu of t, p of t, x, all equal to mu of t, q of t. And we'll try that again. There it is. Okay. So, to use a reverse product rule, we want to combine the left-hand side into mu of t, the integrating factor, times x prime. So that's what we want to get out. On the right-hand side, we'll leave it alone. Mu of t, q of t. To get to that step, we need to match a certain integrating factor. So let's check. If we reverse the product rule, we get the derivative of one and not the other. So mu of t times x prime plus the derivative of the other, not the one. So mu prime of t times x. Now, to match these up, we check the first terms, check. And in the second group of terms, we have the same x, but we need to have I'll show what we'll do here. Mu prime of t equal to mu of t times p of t. So let's verify that if we have this form of mu of t, then it satisfies this equation. So we take the derivative of e to the integral of p of t dt, and that gives us the exponential e to the integral of p of t dt times the derivative of the exponent. Now, when we write the integral here, we have the integral in terms of t, and we're going to differentiate in terms of t, but this t is really just a dummy variable up here. So I'm going to write it in terms of another letter. P of tau d tau, because that integration variable will disappear. It's a dummy variable that we replace with t. How do we do that? Well, as a definite integral, we'd write it as tau from 0 up to t. Now, this may look very odd, but slightly familiar. This is one of the forms of the fundamental theorem of calculus. If we take the derivative of an integral from 0 up to that same variable, all with an integrand of p, then the derivative undoes the integration, leaving us with the function in terms of the outer variable. So we get p of t, and that's exactly what we need on the right-hand side. Okay, so now that we have verified that our integrating factor is the right kind of function to give us a reverse product rule, we can then combine our unknown terms together into one derivative of a product. Okay. Erase all that. And then, to solve it, we have just one derivative on the left-hand side. We simply integrate, simply in quotations, because it may not be as simple as it seems. So, let's make some room a little bit here. We have mu of t x prime equal mu of t q of t. To integrate both sides, we will multiply each side by dt, the small change in time, and then we will integrate over those small changes. So unlike the separable method, we are integrating in terms of the same variable on each side. On the left-hand side, we run into the second form of the fundamental theorem of calculus, where we have, instead of a derivative of an integral, we have an integral of a derivative. And it works in a very similar way, where the integral undoes the derivative, and we're left with the inside, mu of t times x. There is a plus c. As usual, since we have two integrals, but we're going to combine the constants on the right-hand side. Now, this right-hand integral is where most of the work is and may create some difficulty. But if we can complete that integral, we can solve for mu of t times x. This is all the unknown terms we have here. And then to finally solve for x, we divide by the integrating factor mu of t. Okay, so that is a procedure for using the linear method. Let's do a quick check to see which of the following three differential equations are linear. And since we already learned the method before, let's also check to see if they're separable. So, first, look at A. We have x prime equals t minus x. Well, in this case, it is written in slope form already, which means we can check to see if the right-hand side can be factored into a function of t times a function of x. No. As a difference of t and x is not separable. To see if it's linear, we first check to see if the powers of the unknown variables are 1. So, x prime is to the first power, x is to the first power. It's possible, we just need to write it in the correct form. X prime, we add x, we get t. We check x prime plus 1 e of t times x equals t q of t. Yeah. So that is linear. Now let's go on to the second one. First, let's check to see if it's separable. Well, this is actually Newton's law of cooling, which we did in class. And so you can see that the t does not show up explicitly, making it autonomous, which by default is separable. We can treat the k or any constant as a function of t. So it is separable. Is this linear? Again, we look at the powers of the unknowns. T prime to the first power, check there. T, multiplying that out, still to the first power, times k, that's fine. So it potentially could be linear. Let's see if we can write it in that form. T prime, we have a minus kt, so we add to the other side, plus kt, and then a ka, and we checked. We have the form required. This t prime represents x prime. We have a k for the p of t, a t for the x, and a ka for the q. Yes. That is linear. Okay, so the first two are linear. Sure. Let's try the third one. P prime equals rp times 1 minus p over n. This we saw as the logistic growth model. So we know it's separable because we saw that solution before. There's no t explicitly shown. It's another autonomous equation, which is by default separable. Now let's look at the unknowns. P is our dependent variable. P prime is to the first power, so that's a check. We have p is a times 1, that's fine. P times p, that's p squared. There's no way. There's no way that you can write this nonlinear first order differential equation in our linear form yet. We'll look at another method later on to see that this actually can be solved with a transformation called Bernoulli's transformation. But that's for another day.
time.